In this video, we'll look at the law of cosines. So in the last video, we talked about the cases for triangles for which you need to use the law of sines. Now in this video, we'll look at the remaining two cases, do a quick proof of the law of cosines, and then give a formal definition. So we looked at the cases where we had some side, an angle, and another angle, which this one we know can be easily solved just by kind of drawing up those dashed lines. We also looked at a case where we had an angle, some side, and then another side. This one we knew was ambiguous because the length of this side could vary, in which case we could have 0 solutions, 1 solution, or 2 solutions. And for those two, we used the law of sine. Now, for the other two cases, that is when we have a side, an angle, and another side, where the remaining side is something like this, and we have two other angles, and the case when we have just 3 sides, we'll use the law of cosines. And the idea is that the law of cosines puts in relation one angle and a couple sides. So these cases are side, angle, side, and side, side, side. So imagine for a moment that we have this kind of triangle. We know nothing about it other than that we have 3 sides of length A, B, and C. First, let's try to fill in some of the information on this triangle. Let's call this angle here A. Just by convention, we'll call the angle opposite little a big A. And we know that we've oriented this triangle in such a way that A is at 0, 0. Similarly, for angle B, this angle right here, since that angle is opposite of little b, we'll call that big B. We know that this angle B is at the point C, 0, since we're C units over from the origin. Now, for us to be able to go about doing anything with this, it's useful for us to drop down a vertical line so we can create a right angle here. Now this last angle here, C, let's figure out the height at C and the length over from the origin at C. First, I think the height is maybe a little bit more intuitive, so let's call this angle here, we'll call that theta prime. This angle here is theta. So theta prime equals 180 minus theta. And if we take the sine of that, the sine of theta prime equals the opposite, we'll call that just the y value, over the length b. So if we want the height, y, we need to say that this is b sine theta prime equals y. Now, if y'all recall, b of sine 180 minus theta, sine of 180 minus theta is just sine of theta because they take on the same vertical value in the first and second quadrant. So we can just say that this is equivalently b sine theta equals y. All right, so that's a good place to start. So now we've got some of the coordinates here. So this will be b sine theta. Now we'll do a similar kind of process for cosine using the same theta prime. So we could say that cosine of theta prime equals x over b, which would then imply that b cosine theta prime equals x. Now the question is, what happens here? Well, for the same angle theta, we'll have the same absolute value of the horizontal distance away from the origin. So we could say that b cosine of 180 minus theta is the negative b cosine theta, which equals x. And lastly, since the angle theta already brings us into the second quadrant, we don't need this negative sign. So that leaves us with just b cosine theta. Okay, so now let's clear this out. Pick a different color. And now we're going to use the distance formula to help us solve this. So we'll say that A equals the square root of C minus B cosine theta squared plus 0 minus B sine theta squared. Okay, so now we square both sides, so we have A squared equals C minus B cosine theta squared plus negative B sine theta squared. We do a little bit of foiling, so we have C squared minus CB minus 2BC cosine theta plus B squared cosine theta squared plus negative plus B squared sine theta squared. Fortunately for us, if we factor out a b squared from the b squared cosine squared theta plus b squared sine squared theta, we know that sine squared theta plus cosine squared theta, this is just 1. So we can substitute 1 in there. And we are left with b squared plus c squared minus 2bc cosine theta. And this is one of the versions of the law of cosine. So, and of course, in this case, I use theta as a kind of placeholder for a. So we could write this equivalently as that. A squared equals b squared plus c squared minus 2bc cosine a. So formal definition, the law of cosines, in any triangle ABC, we have a squared equals b squared plus c squared minus 2bc cosine a. B squared equals a squared plus c squared minus 2ac cosine b, and c squared equals a squared plus b squared minus 2ab cosine c. A nice way to remember this is for whatever you're trying to solve, consider for example a, you have the other two sides both squared and being added to one another, and then 2 times the two sides being multiplied together and the cosine of the angle opposite of little a. So there's kind of a pattern to what information goes where in these formulas. In the next video, we'll look at an application of the law of cosines to find the area of a triangle.